All right, here's a short video on basic static equilibrium problems and how to set them up. The nice thing is they're very formulaic. If you follow the formula, you can kind of always set them up right. Um, Obviously, the hard part is then like identifying the forces acting, where they're acting, and how that applies. So, static equilibrium is exactly what it's called for. Static, nothing's moving. Equilibrium, everything's equal. So everything is equal to zero, which makes the math kind of nice if you get it set up right. So that means either something's not moving and it's just staying static, or because you want it to not keep moving, or you're trying to get something to move and it's just about to move. One of my favorite examples is the wheelbarrow question, because I did a lot of wheelbarrowing in my youth for my dad, and you would have to wheelbarrow over rocks, up curbs, down curbs, and whatnot, and sometimes you'd run into something and get stuck, and then you'd have to push harder and harder and harder until you actually went up and rolled over the curb or whatever. So that's one of my favorite WebAssign problems, is the wheelbarrow over the brick problem, just because I personally relate to that. So that's one of those that's just about to move. Not moving, if you're trying to build a building and you're analyzing the forces in, like, say, the tension in this beam or this cable or that cable in a bridge, it's extremely important in civil engineering, because if you're building a bridge or you're building a building, you don't want that to move for the most part, or if you do want it to move, you want it to move in a controlled way. So static equilibrium problems come really into play when you're building or constructing stable mechanisms or buildings, right? So everything is zero. So what does that mean? That means all the forces X and Y are zero, all the forces up and down are zero, and all the torques have to be zero. And that's all the tools we get to work with the static equilibrium. Everything needs to be zero in the horizontal, vertical, and rotational dimensions. So that's kind of it, right? Like, everything's just got to be zero. So the math gets kind of easy. So first example, which is really straightforward, is we're going to hold a shelf. Normally I would do this with like some kids in large scale, but I don't have that option. So here's my shelf. I'm holding it with my left hand and my right hand. Now if I'm holding it stable, nothing's moving. So the trick to these problems is identifying a point of rotation for something that's not rotating. That gets a little weird, because like, I got this weight on here. So if it's stable, you could imply that my hand here on the left needs to be applying a bigger force than my hand here on the right, because the mass is closer to my left hand. If I were to switch the shelf and I were to hold it like this, or I were to move that mass around, now my right hand is applying a lot more force than my left hand, because the mass is closer to my right hand. Now that's pretty intuitive. Maybe you would think, right, like if this got closer to my right hand, it would need to support more of the weight. If it got further from my left hand, it would need to support less of the weight. The key is like, it's not rotating, so how do I sum up the torques? Because if this hand, my left hand, applies more force, it can rotate around my right hand. So my right hand could be the point of rotation. If my right hand varied its force, it might cause it to rotate around my left hand, and then that would be the point of rotation. If my hands varied their force, I could get it to rotate around its center of mass by changing those forces in a certain way. So, or heck, I could get it to rotate around, that one's tough and I'm making a weird face while I do it. I could get it to rotate around the mass, not the center of mass of the stick, but the mass. So the point of rotations are endless when something's not moving, which means you get to pick. You get to pick the point of rotation, and you want to pick in a more clever way. You want to pick where one of your unknown forces is acting. So in this example, if I said this is a stick of length L, and the mass has a mass of M2 and the stick has a mass of M1, and I need to solve for how much does each one of my forces in each hand have to apply a force. So I know the length of the stick, I know where the object is on the stick, and I know the mass of the stick and the object's mass. So the question is how are my forces? So what you want to do is pick an axis of rotation, because it's not rotating. Weird. So pick one. Doesn't really matter. Pick a point where there's an unknown force. That's going to make your math a lot easier. And then in this example, you could really pick your point of rotation to be anywhere, because there's only two unknowns, the force from the left hand, the force from the right hand, and we have three equations. We can make this a little more difficult by having a third unknown, but for the first example, let's not do that. So pick the axis of rotation to be around the left hand. Why not, right? So it's going to rotate around this point, even though it's not rotating, and that's how I'm going to set up my equations. So then sum of forces in the x is 0. There are none. Weight forces and my hand forces are vertical, straight up. So no forces horizontally. Forces in the y, I'm going to pick up to be positive, so the two up forces, oh, can I point? Left and right are up, and then the two weight forces are down and negative, and those add up to 0. So there's one equation from the sum of forces in the y, and I have two unknowns, so I need a second equation to be able to solve for those. So then I move to my torques, since my sum of forces in the x didn't help me out. So sum of torques, pick the point on the left to be the axis of rotation, and sum your torques up from there. Again, the point of rotation doesn't matter, but you got to pick one and then stick with it. So sum of forces, then my left hand then applies no torque because it's 0 distance from the axis of rotation. The weight of the stick causes its own rotation, right? Even if the mass wasn't there, the stick would still cause its own rotation through its own weight. So we've got m1 gl over 2 acting at half the length of the stick. And then we know maybe that m2 is x distance away from the axis of rotation, so we got m2x. And those are both trying to make it rotate in the towards me direction, right hand rule. And then the force on the right is, someone erased my L. The force on the right is acting up, causing a counterclockwise rotation, or a towards you rotation. And that's acting at L, which somehow got erased when I was moving my whiteboards around. So you can't see it. So the force on the right is acting on L, and all those torques got to add up to 0, so it stays not moving. So then you can see in my torque equation, I only have one unknown, the force on the right, so I can use my torque equation to find the force on the right, and then I can go to my forces on the x the y, to solve for my force on the left, and then I'm done. And that's the general approach, right? Kind of draw a free body diagram, pick an axis of rotation, and then see what your equations give you. Well, that makes sense. Let's do slightly more difficult one where we actually have some forces in the x. I have this precarious setup here on my wall. So I have my meter stick. I got a weight here on the meter stick acting some distance away. I got a tack in the wall from where there used to be a picture. Got a string, it's causing some angle here with the stick. And the stick is actually just using friction to stay point. It's not fixed at all. I hesitate to show that, but I will. So I can actually take it off the wall and then put it back. There's nothing holding that up. And of course now this is gonna fall, and it'll be just like class when my demonstrations crash to the ground. So this one's a little more complicated because we got more forces acting. We got an angle happening here. Hard to see in the video, and I eliminated it from the example problem, but there is a slight angle there made with the wall as well. So we're just using friction to hold it up. And what's interesting, right, is that if I were to move this mass around, I would change the forces acting on the wall and the stick, and everything would change based on where this mass is acting. If I move it further out towards where the string is acting, then the tension in the string would actually get bigger. Just like moving it towards one hand or the other would make that hand's force get bigger. So big force over here, bigger force over here. So by moving it further out, I could cause more tension, and then maybe the string could break. Interesting thing is the string is also pulling it towards the wall. So if I increase the tension force, I also increase the amount of pull towards the wall, which is going to increase the force from the wall, the normal force from the wall, which will increase friction. So actually moving it further out makes it more stable by increasing the tension force, which then increases the friction. I touched it. Increasing the friction acting on the wall, and everything then has a better chance of staying in equilibrium. If I were to move the weight closer to the wall, the tension would get less, and then we'd have more force here, which would need more static friction, just like moving it closer to one hand or the other would cause more upward force needed, which in this case is static friction. But I don't get a static frictional max without more normal force. So a lot of things happen here. As I move that closer to the wall, I get less normal force, I actually get less maximum static friction force, and then my chance of that slipping gets bigger. So moving it towards the wall makes the static frictional force smaller, and the chances of that part slipping and it not becoming stable. If I move it closer to the endpoint, then I increase the tension, and I might actually increase the tension force to a point where the string could break. So position of this mass on my little meter stick ramp here, I like to think of it as a drawbridge because that relates to some WebAssign questions too. Changes the, I'd say dynamics, but nothing's moving, the statics of the problem. So let's take a look at the equations. Try not to knock that over. So what do we got going on? Sum of forces in the X then are the normal force acting to the, man, this messes me up because I'm always used to teaching using my left as your right, so it makes sense to you, but then the screen and the double flip. But either way, we've got the normal force acting to the left. No, the right. To the right. We have the normal force acting to the right, so we're going to call that positive. We got the tension component acting to the left, t cosine theta. Those are only horizontal components, so that adds up to 0, assuming no angle made with the wall. Sum of forces in the y direction, then tension is acting upwards with t sine theta. Static friction is acting upwards near the wall, upwards, so positive. And then we've got the weight of the stick itself down, negative, and the weight of the attached mass down, negative. And then all of that gets set equal to 0. So we've got that in our sum of forces in the y equation. I didn't substitute it in mu normal for my static friction. Maybe the question would ask something about like, what's the maximum position you could find so that it doesn't slip? Or maybe it says, you know, if we put the mass here, what coefficient would we need in order for the system to not slip and stay stable? So this may or not be a necessary step depending on the way the question is phrased. Normally, static equilibrium questions are about exploring those limits where, when will it start to move? What range of positions can we have so that it stays static? So then we want to explore maybe how far can I move this out before the string breaks, or how close can I get it to the wall before it slips? And then that comes into play with our torques, right? Where the position of the mass is determines on the torque it's making, and then that will determine whether it will start to rotate or not. So then sum of torques, boom, we are going to choose our axis of rotation to be the wall because there's two unknown forces. There's our frictional force and our normal force, and they're definitely related, but we have two unknowns acting in that position, so we want to choose that to be our axis of rotation. That is generally the good advice, right? Anytime there's unknowns acting or more than one unknown acting, pick that to be your axis of rotation for your torques. And that'll usually set up your math to be a lot easier. So then what we got? We got the weight of the stick, M1G acting at half the length of the stick. Excuse me. We've got M2GX, so its position, we don't know where it is, but we're going to measure it relative to the axis of rotation. And maybe we need to solve for that. Maybe we're given an x and we solve for mu. Maybe we're given a mu and we solve for x. Depends on the way the question is phrased. Just going through the general setup here. And those are both going to be positive torques because they're causing it to rotate towards me or towards the wall. We're going to call those positive torques because why not? Doesn't matter. Arbitrary. The tension then is pulling the end of the stick up, causing the rotation the other direction in the towards u direction using the right hand rule. So we're only going to use, right, torques are cross products, so we're only going to use the perpendicular component of the tension, t cosine theta, times then the full length of the stick where it's acting, and we're going to set that all equal to 0. So the general unknown forces are just the normal force and the tension, which I've underlined. So we have 3 equations and we have 2 unknowns, which means we do have room for a third unknown. And like I've said in the past or a second ago, that could either be mu or that could be x, depending on the phrasing of the question. They could say mu static is, what's the maximum x could be? Or they might say x is, how sticky does the wall need to be so it doesn't slip? So x or mu could be our third unknown here. And that's kind of it for that one. Yeah, it didn't fall yet, so that's fun. So general strategy for all static equilibrium questions kind of goes like this. Draw a free body diagram at the points of application, right? So not a normal free body diagram where you just draw a dot and you draw the forces acting on the dot. That'll only tell you what the center of mass will do, and we already know the center of mass isn't going to do anything. It's going to stay static. So we want to draw the forces at their point of application so we can determine their torques, right? The next thing to do is then choose an axis of rotation so that you can figure out where your unknown forces are. So choose an axis of rotation somewhere where there's unknown forces or more than one unknown force. That'll make your torque equation simpler and then make your algebraic process easier as you go through to solve for your other unknowns. Break all your forces into x and y components, right? Because we're summing up forces in x and y. So any force at an angle, you're going to break that into horizontal and vertical components, and then you're going to set up your three equations. And that's kind of the main crux. Sum up the forces in the x, sum up the forces in the y, and sum up your torques. See what you get because you're done doing physics, and then you just have to do a bunch of algebra to solve for whatever you need to solve for. There is a very formulaic way to do static equilibrium problems. Boom, boom, boom. 5 steps. Kind of went over them here. Check out the WebAssign help problems, and we'll go through a whole bunch more of them. Stay dynamic. Whatever.